Stokes Law and terminal velocity. Very often in physics we're dealing with very complex situations, and the way an object moves through a fluid is one of these cases. Take for example a parachutist, or a boat moving through water. One way forward can be to make some simplifying assumptions, to develop a theory, then see how predictions based on this theory match experimental evidence, possibly adapting the theory as we go. The theory can sometimes give valuable insights into what is happening in more complex situations. Sir George Stokes investigated a simple case of objects moving through fluids. He investigated small spheres moving at low speeds. He took a sphere of radius r, falling through a liquid of viscosity eta. By marking out a known distance and timing the sphere to cover that known distance, we could work out the velocity of the sphere. Let's look at the forces on the sphere. Well, the weight would be acting downwards, and upwards there would be the upthrust and the viscous drag. If the sphere was moving at its terminal velocity, the weight downwards would equal the sum of the upthrust and the viscous drag, meaning there is no resultant force on the sphere. He found that the viscous drag was given by this expression, where the viscous drag F is equal to 6 pi times the radius of the sphere times by the coefficient of viscosity of the fluid eta multiplied by the velocity of the sphere. This is known as Stokes Law. This formula is provided on the datasheet. Stokes Law allows us to work out the units of the coefficient of viscosity eta. Here we have the Stokes Law expression again, and rearranging for eta we find that the coefficient of viscosity is equal to the force over 6 pi rv. The force will be in newtons, the radius in meters, and the velocity in meters per second. So, putting in the units into this expression, we get the units of eta will be newtons times seconds over meters times meters. This simplifies to newtons per square meter times seconds, but the newton per square meter is the Pascal, so we can give the units for the coefficient of viscosity as Pascal seconds. Stokes' law also allows us to work out the terminal velocity of a sphere. We said that at terminal velocity the weight is equal to the upthrust plus the viscous drag. The weight of the sphere, which I've called W sub s, is equal to the mass of the sphere multiplied by the acceleration due to gravity, but the mass of a sphere is given by its volume times its density, the volume of a sphere being 4/3 pi r cubed, and this then is rho s, the density of the sphere. To find the weight then multiplied by the acceleration due to gravity. The upthrust is equal to the weight of fluid displaced, which I've called W sub f, and this gets the same expression as above, but with the density of the fluid in place of the density of the sphere. This comes from Archimedes' principle. The viscous drag we've just found from Stokes' law, F equals 6 pi r eta v t here for the terminal velocity. So that is Stokes' law. And putting these expressions together into this, we get that the weight of the sphere is equal to the upthrust plus the viscous drag. Rearranging for the terminal velocity, we get this expression, and then we can simplify to find that the terminal velocity of a sphere is equal to 2 times its radius squared times the acceleration due to gravity multiplied by the difference in densities of the sphere and the fluid, over 9 times the coefficient of viscosity of the fluid. So, the larger a particular sphere is, the greater its terminal velocity.